Hello everyone, my name is Nantabana Shiba and we are working as a team of 3 on our AI project. There is Musimenta Tendo Divine and Chomjuni Edna, and the title of our project is Knowledge Graph-Based Spatio-Temporal Intelligence for Real-Time Campus Crowd Detection and Recommendation. So the keywords in our project, we have knowledge graphs, spatio-temporal modeling, campus crowd management, graph neural networks, fairness-aware recommender systems, and privacy-preserving geolocation analytics. So these are the contents of our presentation, and we are going to begin right. Our system is going to be able to detect crowds at the different service points. Let me say the ones that are on high demand, like cafeterias, libraries, Wi-Fi spots. Then recommend alternative spots that might be less busy. So here we are going to introduce a campus crowd detection and recommendation system that is going to help us manage crowd densities on the university. So we are going to integrate knowledge graphs, spatial temporal modeling, and then real-time geolocation analytics. In that the system is going to use geolocations to detect crowds, to detect the presence of crowds at a given place in a given time. If we make a literature review of our project, we are going to define the different keywords. We have knowledge graphs. Knowledge graphs is a structured way of representing information as an interconnected network of entities and their relationships. It's going to help us map concepts and their relationships in a way that the machine can understand and use the knowledge effectively. Then we have graph neural networks. Graph neural networks is an example of artificial neural networks that is able to use data that is structured in form of graphs. These graph neural networks are going to help us make sense of the noisy and irregular geolocation data and the sensor data that we're going to use for our project. Then spatial temporal modeling. Here, this looks at the way things change across space and time simultaneously. So this system is going to be able to detect crowds at different places in a given time. Then there is fairness aware recommender systems. This is a recommendation engine that does not only look at accuracy and efficiency, but also makes sure that services and resources are equitably distributed. For example, if cafeteria A is crowded, this system won't only recommend one cafeteria. It's going to recommend other cafeterias such that the crowds are equitably distributed. Then we also have privacy preserving geolocation analytics. Here it's analyzing geolocation signals, the Wi-Fi logs in a way that protects the privacy of the campus students or of an individual. So if we look at the related works and the recent trends that relate to our project, we have in the paper dynamic graph convolutional crowd flow prediction model based on residual network structure. They proposed a model that integrates spatial attention and temporal models to predict urban inflow and outflow. There is also Another study, spatio-temporal complex graph convolution network for traffic flow prediction. It highlighted the value of graph-based deep learning for capturing complex temporal spatial dependencies in mobility data. These models, or these other works, they look at spatial temporal modeling, they look at fairness aware recommender system separately, but our project is going to come in and integrate all these things into one thing. Then our problem statement. Here, the domain application problem. Here we have a difficulty in effectively managing dynamic crowd densities on university campuses. So this leads to service inefficiency, campus safety risks in those crowds. They might involve some criminals. Then this happens at the high demand areas. Let me say the cafeterias during lunchtime, they're usually overcrowded. So here our computational problem is to model, predict and manage spatial temporal crowd dynamics on university campus. So we are going to use noisy, incomplete and irregular geolocation data, but while ensuring fairness and privacy in these generated recommendations. So our input here, we are going to use real-time geospatial signals. Let me say the geolocation data, the Wi-Fi logs, the IoT sensor readings. Our output, real-time forecast of crowd densities and congestion risks, real-time detection of crowds. So it's a personalized yet fair recommender. So here our objectives include to develop a campus crowd detection and recommendation system, integrating the knowledge graph driven spatial temporal modeling with real-time geolocation analytics, to estimate, predict and balance crowd flows across campus facilities using advanced AI models, then to generate probabilistic density forecast, dynamic heat maps, congestion risk scores, and waiting time predictions. So here our overall objective is to improve the student well-being, service efficiency, and comfortability. Then this is our system architecture. We have data collection and pre-processing, mobile devices. These ones are the ones that are going to give us the locations. And we have the Wi-Fi access logs, in that when someone is logged in to a given Wi-Fi, we can be able to detect their presence. So here is our knowledge graph. Then here we have the graph neural networks. So this is our graph-based recommendation engine that looks at fairness constraints and avoids overloading. So this is basically the architecture of our system. So here, if we look at the dataset description and exploratory data analysis, we are using a dataset that we got from Mendeley, and it's a vast ADMA dataset for spatial temporal genes. It has over 200,000 rows and 10 columns. So the features here of our data, we have the ID of these moving entities. This data set, it has pedestrians, vehicles, buses and bikes. It has their geolocation data, that's the X and Y coordinates, the speed, the acceleration, mobility and dynamics. We also have a cluster ID. So Here it's going to help us model real-time crowd flows and densities. We are going to use this geolocation data to get a model that detects crowds at the different service points. Then it also enables knowledge graph construction from these clusters and entities, and then supports crowd management simulation in campus environments. So this is the basic information about our data, the columns and their data types.
Hello everyone, this is Mosimeta Tendo Divine from the group that my colleague has mentioned previously, and we are going to continue with the exploratory data analysis. And here we examine the general structure of our illustrative data set of the geolocations, and we found out that it has 207,315 entries across 10 columns, and all columns showed not now as the previous slide showed you. And then this is vital for our projects that deals with geospatial data from Wi-Fi, mobile phones and IoT sensors is often noisy and incomplete and irregular, and it requires robust processing. So the label column has an int data type which can help us to say the status of the crowd, whether the crowd is congested, normal, yes, in a numerical conversion for our graph neural network. We observe the few rows of this data set, and it reveals columns like ID, which is an object, and this can stand in for the anonymized ID for the geolocation dataset, then the time step, which can stand in for the timestamp, then the x coordinate, which is the longitude, then the y coordinate, which is the latitude, the heading, the speed and acceleration, etc. These features are highly relevant because they represent spatial-temporal and dynamic characteristics directly analogous to the type of geospatial signals we collect from the mobile devices, Wi-Fi logs, and IoT sensors for our particular campus crowd detection system. Understanding these basic features is foundational for our knowledge graph construction, where ID would relate to the anonymized user ID or sensor ID, X and Y to the approximate location or fixed location, then time step to the timestamp as you saw earlier. So we used the code below to view the data set, how it is, the dimensions, the data types, and the first few rows, as you can see, the like 5 rows that have been given in the image. Then we continued with data cleaning, and we use the following codes to check for missing values and count them and sum them up. As you can see in the picture, acceleration has 668,162 missing values, and then we were able to replace, if you run this line of code, it can be able to replace those values with 0.5 and use that data, because we realize that removing it may not leave us with sufficient data to use. Then we continued with the analysis, and we got the basic descriptive statistics about our columns of the geolocation data, like the count, the mean, the standard deviation, minimum value, maximum value, the quartiles. And for our project, applying this describe data set to combine applying the describe code to our combined data set with Wi-Fi and IoT sensors will help us to understand the range and distribution of the occupancy count from the sensors or connection duration from the Wi-Fi. For example, the mean and maximum values for X and Y define the geoscope of movement, which in our project would delineate the campus boundaries and potential campus facilities, pathways, student clusters, and become entities in our knowledge graphs. As you can see there, all the mean, count, standard deviation, percentiles, all the data was given to us through the describe method. So we went to data visualization, and to visualize the spatial spread of data, we have histograms for the y, which is the latitude, and the x, which is the longitude. These show where observations are most concentrated geographically. In our campus crowd management projects, similar histograms are derived on locations from Wi-Fi IoT sensors, would reveal areas of high student activity and specific campus facilities that become entities in our knowledge graphs. So those are the graphs, that is the y against the count. As you can see, the time step, which illustrates the temporary distribution of data points from our system. For our system, a consistent distribution over time is critical for building reliable temporal transitions within the knowledge graph and ensuring the accuracy of temporal reasoning layers in our graph neural networks, which are designed to capture the time-dependent nature of the crowd flow. Then we continue with the visualization with the histograms. Then this histogram displays the ID against the count and per unit vehicle, pedestrian, or what. In our system, this is analogous to understanding the frequency of activity per a normalized user ID from Wi-Fi logs, IoT sensors, GPS locations, or from IoT. It helps us gauge the contribution of different entities and identify potential dynamic student clusters in our knowledge graph. Then the other histogram is the heading. This histogram shows the distribution of vehicles, pedestrian directions. For our project, understanding the predominant directions of movement, even from aggregated Wi-Fi, IoT sensors or geolocations, is key. This informs the pathways, entities, and temporal transitions edges in our knowledge graphs, helping us to predict where students are likely to move and thus where crowds flow will increase or decrease. Then we continue. This is just exploring the relationship between the different features, how they relate, how they increase, how they appear against each other. So we typed that code above to plot. It's a pair plot which pairs different features with the other. That's why you see the horizontal line has features and the vertical line has also features against each other, to show you that as this increases, this also increases, or this remains constant, something like that, depending on the number of people in the area. So then we continue with the correlation heat map, which visualizes pairwise linear correlations between numerical features in the geolocation data. We see a strong positive correlation between speed and acceleration, which is expected. In high correlation between x, a very high correlation between x and y, which is 0.9, as you can see there in the graph, indicates tightly coupled geographical movement, suggesting confirmed areas or linear paths, which is a characteristic of campus pathways. This helps us to define pathways, entities, and semantic relationships in our knowledge graphs, as you can see. So let's continue.
Hello everyone. So my name is Somjun Edna, and I'm going to continue from where my colleague has stopped. So I'm going to be starting with model selection and deployment. So basing on our need to develop a campus crowd detection and recommender system, we chose a density-based spatial clustering of applications with noise model, which is an unsupervised density-based clustering algorithm which naturally groups points where many devices are close together without necessarily requiring crowd labels. So in this way, this model works well with our dataset that actually has no crowd labels, like it has no data labels for the crowd. So, and also it's good at handling noise, like noisy data. So
for this model, it automatically classified isolated points as noise, which in this way it avoids scattered individuals being considered as a crowd, like scattered people who are not actually close to each other. It ignores them, labels them as noise. So looking at this model's architecture, it's actually built on density rules. So this is how it works. A point is picked out and its neighborhood is determined using a radius parameter epsilon. So here we're using model, we're using epsilon equals 5 value. So meaning we would choose a point that is plotted, then determine a radius around it. So if another point lies within that same radius, the epsilon of 5, then it's considered part of the same neighborhood. And points within the same radius, the epsilon, make up to the mean samples. The mean samples here, I mean like the minimum number of data points within the same radius to actually consider that as a crowd. So points within the same epsilon that make up a mean samples of 10 are core points and form a cluster. So other points that are close but do not meet the density rule become border points, and for those that do not fit into any cluster are labeled as noise, like they're not put in any cluster, they're just labeled as noise. So that is how our system is able to identify the crowds cluster, different devices that are close to each other into clusters, and also use threshold values to determine whether the place is crowded, moderately crowded, or not crowded. So going to the deployment pipeline, the deployment pipeline is like all those processes from acquiring data from the data sources up to obtaining an output that you want actually the system to deliver. So in this deployment pipeline, we have data ingestion. Data ingestion is what is like, how is that data acquired, and like how is it acquired, transformed into something that the model can use. So and then we have data cleaning and pre-processing. This is dealing with noisy values, missing values, and in this case you are substituting all the missing values with a certain value, or you can choose to do the median. Yeah, that makes it more accurate. And then after data cleaning and pre-processing, then we employ the clustering model that does the clustering, that clusters points, different geolocation points into clusters to make crowds, to determine whether the place is crowded, moderately crowded, or not crowded. Then it goes ahead to recommend other alternative places that are less crowded. Then can also do evaluation. Evaluation is actually like determining the model's performance, and then after it goes to the output, how are we able to deliver the output via, of course, via APIs and a mobile app with an interface, so a person can be able to choose the yes. So going on to the evaluation metrics, it shows the kilowatt score. This one measures how similar each point is to its own crowd compared to its own cluster compared to other clusters. So this score gives a quantitative measure of cluster cohesion versus separation, and this helps to tune the model parameters, the epsilon, the mean samples, to get meaningful cloud clusters, like how close are those points to their own points in the same cluster, and how far are they from points of other clusters. This helps to distinctly map out clusters. And then the evaluation result was 0.99 and other figures, which is almost equal to a 1, like approximately equal to a 1. This means it's a good outcome, and it means that the devices in a cluster are indeed grouped closely together. And then the Davis-Baldwin index, it evaluates all clusters together in terms of compactness and separation. It helps to determine whether the different clusters are distinct. like how far are the clusters not overlapping, like are they overlapping or not overlapping. And if the value, this works when the value, it shows actually when the values are very low, meaning the clusters are tight and well separated. So, and we are looking at a scatter plot, and the scatter plot we have, it actually shows 3 clusters, the one in blue, the green one, and the orange. So the scatter plot illustrates how our clustering model groups different devices across the area based on geolocation signals. So each color represents a different crowd cluster. So this shows that the model is able to separate different groupings into distinct crowd zones. So meaning it will be able to work for our system. So, and then we have the heat map of the crowd density. It shows where most devices are concentrated in the area, where we see this very concentrated red zone. It shows the most concentrated part, which might symbolize a main hotspot, like a place that has a lot of traffic. And then the other points around here and here that are show minimally smaller light spots that show secondary less dense gatherings. Then going to the demonstration of the developed product. Actually, our product name is Campus Crowd Detection and Recommender System. Then the goal is to help students avoid crowded areas, reduce waiting times, and support the campus administrators in planning and reallocation of services and facilities or resources. So the key features, we have real-time crowd monitoring, predictive crowd forecasting, fair and personalized route and service recommendations, plus privacy preserving design. So if you look at, this is how our system is supposed to work stepwise. We have data collection. It collects data from mobile devices, the geolocation, the Wi-Fi logs, and IoT sensor data. Then it does the data processing, cleaning, and normalization and scaling. Then it uses knowledge graphs to map out the facilities, paths, student clusters, temporal and context search. And then we go to the graph neural network and the density based model that does the crowd detection and the forecasting and all the clustering to actually determine the places that are crowded, less crowded, moderately crowded. And then the recommendation engine that actually uses fairness awareness, that is fairness aware, to actually reallocate, like give people alternative service points to go to. And then then the final output or product is going to be like delivered either on a student app, that a person is actually able to get the highlights of the crowds around campus, and also an admin dashboard that helps the administrators to actually visualize the crowds around facilities so that they're able to allocate resources. And then explain the IP assets. We have, okay, IP assets like intellectual property assets, like these are creations, innovations, and proprietary resources that make our system unique, protectable, and variable. It could be data assets, the raw campus location collected from the devices, Wi-Fi logs, and IoT sensors. Since it's the data collected by us, so it belongs to us like original. Then our system architecture has been built by us, and the privacy and security mechanism that actually keeps the identities of the students confidential. And then looking at the conclusions and limitations. Conclusions: successfully developed novel system integrating knowledge graphs, spatio-temporal machine learning, and fairness aware recommendation for effective campus crowd management. Significantly contributed to improving student well-being, service efficiency, and campus safety. It also provides actionable analytics for campus administrators, enabling data-driven decisions, how to reallocate resources to different places. So the system is scalable, interpretable, and context aware. Like, it can be expanded or improved, or expanded, like to be better and add on the area boundaries. So the limitations: predicting unforeseen anomalous events. The model might struggle with sudden high anomalous events, either unexpected facility closures or protests not captured in historical data and contextual factors. So the counteraction plan is integrate real-time social media monitoring and emergency alert systems as additional data sources to capture immediate and structured event information. So-called start problem challenges. Challenges that arise for new campus facilities, pathways, or events lacking sufficient historical data for training. The counteraction plan would be employ transfer learning from similar existing entities, or implement rule-based fallbacks and initial conservative recommendations until enough data is collected. And then the next steps will be expand data integration, enhanced predictive models, personalized recommendations, proactive intervention systems, and broader applicability. So that was all. Thank you all for listening.